Morning. How you doing today?
Good, how are you?
All right. So Jacob and Jalala, can you hear me okay? Can you see the screen?
Yeah.
Great, thanks. I've been on a bit of a streak, it seems like, where either the video isn't working or the audio isn't working, so.
Yeah, there's been some other teachers that I've had that have been having some trouble as well lately, it seems.
Oh, really? I figured it was just me. Yeah, I figured out if I come early, then I don't have any problems. If I don't come early, then I always have a problem, so. Good morning.
Morning.
Hey, where did you find the literature KBQ?
Oh, for the lab,
Yeah.
for the lab, I hadn't even looked at it.
Oh,
I was so far behind in that lab.
no, I was too, my data was so messed up.
Yeah. Yeah, I hate when she does that. She did that all last year for like, where there was virtually no explanation.
Yeah.
My data's off and I haven't had a chance to really look at it. I think it's either in, I think it's just online. We just have to look at
I like looked it up, but I couldn't find it.
Really? I don't know. I haven't looked into that. I'm just saving it for the weekend.
What are you looking for?
The literature KEQ for FESCN.
Yeah, it would be the equilibrium value of this reaction we did.
Yeah,
And, I don't know.
We're like comparing what we got to the literature.
so that's not in the back of the textbook?
Would it be in the back of our textbook?
It could be.
I
Okay.
I think there's some equilibrium tables in there, I thought.
I had even, between taking two labs, chemistry labs, I have a hard time keeping track of what we're doing. I was going to take an exam after that, so I was just like, all right, I'm not leaving.
I don't know how our lab is so different than the other two.
Oh, is it?
Like they only each do like a half of the experiment every time. And like this time they didn't, like Erwin gave them all the answers for the data. And he,
Oh, the one that Dr. Donovan teaches?
yeah,
Oh, okay. Yeah.
like they didn't have to do the like all the questions. No fair.
I think out of all the like pre-med classes and classes for my bachelor's degree, bad lab last year for organic. It was the hardest lab I've ever been through. The hardest class with the most amount of effort needed to put forth for one credit.
For her?
Yeah. Yeah.
Is it better? Than-
Oh my gosh. Yeah. Yeah, he's Dr. Groban, I really enjoy talking to and learning from, but yeah, her lab was just crazy. The amount of work she went with.
I just wish we had more time.
That is, yeah, now that they split, I really wish they would have looked at that a little better.
Because I can never finish it in time.
Yeah, because our lab's supposed to be 3 hours, but they split it in two to coordinate. And
Yeah.
It seems like some of the labs weren't adjusted to fit that time frame.
Yeah.
It'll be 90 minutes and I'm like, maybe 2/3 of the way
Yeah.
down.
Seriously.
Yeah, so that's a little aggravating because then she expects us to come in
At a different lab time.
at a different lab time. It's like a totally different day.
Yeah, and I always have like physics during the other lab times.
Yeah.
Oh, good job.
I didn't know Groban was teaching. This semester.
Just lab.
Just the lab.
Because he's this something.
Yeah, Professor Namani passed away last year.
Okay, I got you.
And then since I'm teaching instrumental analysis and instrumental lab, because I did Gen Chem last semester with the lecture, but this semester I'm not doing it because I'm doing instrumental lab.
Gotcha.
So they needed to come up with someone. And there was another adjunct who you had, Susie, who you had last semester. She chose not to teach this semester because her husband teaches here and he was doing sabbatical. So they were going to do some traveling and stuff. So that's how Professor Groneman got to get the opportunity to teach Gen Chem. So
I know, I did redo it last night because it didn't take my own grade. I know, I was so frustrated.
I looked like a mess. It's not letting her at all.
okay, we're going to go ahead and get started. What the plan is for today is we'll finish up chapter 19, the thermodynamics chapter. And then I think we'll have some time to get started on chapter 20, which is electrochemistry. And then I wanted to remind everyone that on Tuesday, so next Tuesday, April 6th, we'll have a quiz number 4 on that will cover chapter 19. So on Tuesday, we'll have a little bit of lecture. So on Tuesday, we'll have a little bit of lecture, continuing on with the electrochemistry, and then the rest of the period will be an online Canvas quiz. The other thing I wanted to just mention is since we are into April today, kind of in the home stretch of the semester here the last month, the final exam for this section is Thursday, May 6th from 8 to 10 a.m. And that final will be given during that time period, that 8 to 10 time period, and it'll be online Canvas like we've been doing the exams. So once again, today we'll finish up chapter 19, and then we'll hopefully start on chapter 20, which is electrochemistry. Tuesday, we have a quiz number 4. Tuesday, we have quiz number 4 covering chapter 19. And then, as I said, the final exam for this class will be Thursday, May 6th from 8 to 10, and that'll be a Canvas online exam. Okay, so last time we talked about the second law of thermodynamics today we're going to talk a little bit about the third law of thermodynamics. So the third law of thermodynamics simply says that entropy of a pure crystalline substance at absolute zero is zero. And so this means that the atoms or the molecules are in what they call a perfect state. And so from a thermodynamic property perspective, it means there's just one microstate. Remember, we talked last class about microstates and how if you have the vibrations and you have the movement and all this kind of stuff, that you can have all these multiple microstates and it gets pretty complicated pretty quick. Well, if you take it down to 0 Kelvin, and that's what's considered absolute zero, is 0 Kelvin, then there's only one microstate. So this is important in terms of thermodynamic calculations and things like that. But in reality, from a practical point of view, you're not at 0 Kelvin very often, right? That's pretty, remember 273, you had 273 to Celsius to get Kelvin. So that's minus 273 Celsius. So that's not, it's good for theoretical calculations and that, but in reality, you really don't see that. Where this kind of comes into play is, and I think you can probably see where this is headed, is we'll get to the point where we can do some calculations around entropy. And so we're going to have something called standard molar entropies, S, with a zero with it. And what that tells us is that because elements really aren't at 0 Kelvin, which is that reference thing, the values are not zero when we're, say, at room temperature, which would be 298 Kelvin. So that's the reason why when you see these tables for the molar entropies, they won't be zero. Just a couple things which go along and are consistent with what we said before. Standard molar entropy for gases, those values are in general higher than liquids and solids. That makes sense. We've said all along that there's the most randomness with gases. Standard molar entropies increase with molar mass. Once again, that's consistent with what we said before. You get to the bigger molecules, you have more microstates, things like that. And then finally, standard molar entropies increase with the number of atoms in the formula of a substance. Once again, that makes sense too, because you've got more bonds and things like that. So conceptually, none of this really should be new. This is consistent with what we've been saying before. These are just a table in your book of some values, so you can kind of get a feel for it. The big thing I would just point out is the units. It's joules per mole Kelvin. So if you're doing calculations with that, remember sometimes they give us these values in kilojoules, sometimes in joules. And so you want to just make sure that you're working in the right units. Okay, here are some homework problems I'd like you to take a look at. There's one that I will just go over briefly before we move on, and that is number 1923. So let me see what that one is. Okay, so here we're told that the boiling point of Br2 is 58.8 degrees C, and the molar enthalpy of vaporization, the delta H vaporization, is 29.6 kilojoules per mole. And the first question is, when the Br2 liquid boils, does its entropy increase or decrease? So hopefully you're all thinking increase, because we're going from that liquid state to that gas state. So in general, as you get to the gas state, more randomness, more movement, things like that. The second part of the question The second part asks us to calculate the value of delta S when 1 mole of Br2 is vaporized at that temperature. So remember, we had a relationship of delta S equal heat, basically, divided by temperature in Kelvin. So we're given this constant, this 29.6 kilojoules per mole constant. We're told we're working with 1 mole of material. So to get the numerator into kilojoules, multiply 1 mole times that 29.6 kilojoules per mole. And the denominator, that needs to be in Kelvin. So we would take our temperature, 58.8, and add 273 to it to get 331.8 K. And then do that math, and we get a value of 0.0892 kilojoules per Kelvin, or 89.2 joules per Kelvin. So pretty straightforward calculation. Just wanted to point out this relationship is delta S equal heat divided by temperature, and make sure you're familiar with that formula. So what we're going to do now is we're going to move on to calculating entropy changes, and then we'll introduce another term that's new to us called Gibbs free energy, which is delta G. We'll get to that a little bit later this morning. But what I want to point out with like this delta S calculations and some of these others, they're kind of similar to the delta H calculations that we did before. Okay, so that common theme is products minus reactants. And that's real common in this type of calculation when you have that delta, because you're looking for the differences. So entropy change would be delta S would be equal to the sum of the delta S values of the products minus the reactants. So once again, this is pretty much the same type of calculation we did for delta H's. Remember we were calculating those heat values a while back? And so in this formula, and we'll go through an example here in a moment, but in the formula, you see there's a sum of the delta S of the products with that N in front. One of the things you need in these types of calculations is you need a balanced chemical equation. And so you would look at that balanced chemical equation, and then based on the coefficients in front of the products and the reactants, you would, if it's 1, then you don't have to do anything, but if it's a 2 or 3 or something like that, then you have to multiply the delta S value of that product or reactant molecule by that coefficient, okay? Like I said, once again, very similar to what we did for the delta H stuff. So if you remember that and you were able to do that, shouldn't have any problem with this. Okay, so let's just kind of walk through some concepts here. So when we talk about entropy changes, so when we were talking about delta H, we were talking about heat flowing in, right? And so when we did our first chapter on thermodynamics a while back, we talked about heat flow, and we did heat flow calculations in that. Now we're realizing that reactions go or don't go based on heat, but also based on entropy, on this randomness. And so now what we're going to start doing is we're going to start incorporating both of those types of things into how we evaluate it. And so if you think about it, if you have heat flowing into or out of the system, that's going to change the entropy, right? Because we've said as temperatures go up, entropy increases. So it makes sense that if you're putting heat into something, entropy is going to go up. If you're taking heat out, entropy is going to go down. That entropy can affect the reaction. Okay, so if we have an isothermal process, remember isothermal process means the temperature is not changing. And so the delta S of the surroundings equals the heat of the surroundings divided by temperature. And if, remember, the heat of the surroundings and the heat of the system are equal but opposite. And so we have a negative sign here. that says that's equal to minus Q system divided by T. So what this allows us to do is to relate delta S to either the system or the surroundings. So at constant pressure, the heat of the system is simply delta H for the system. And so then we can rewrite our expression for a constant pressure, and this is the relationship we see at the bottom of the slide, that delta S of the surroundings equals minus delta H of the system divided by T. So now we're starting to get this relationship of how delta H and delta S interact. Okay. So when we think of the entropy change in the universe, remember the universe we're defining as the system and everything around it. So the system and the surroundings. So that means that the delta S of the universe has to equal delta S of the system plus delta S of the surroundings. We said earlier that if something's spontaneous, then delta S of the universe will be positive. So now let's take some of that information and we'll be able to generate some new expressions. And this is going to lead us to that new term, that Gibbs free energy term. And like I said, Gibbs free energy is allowing us to tie together delta H and delta S. So we start at the top here and we say delta S universe equals delta S system plus delta S surroundings, okay? Then we can do that substitution that we just worked through a couple slides ago, and we can say delta S universe equals delta S system, and now we're substituting in this minus delta H system divided by temperature for the surroundings, okay? And we get that second equation on the slide. If we multiply both sides by minus T, then now we have minus T times delta S on the universe on the left-hand side. Then we'll have minus T times delta S system for this first term on the right side. Multiplying the minus T to the third term, the T's cancel, the negative becomes a plus, and now we have delta H of the system, and it's positive there. We can go and rearrange this, and by rearranging, all we're doing is putting the delta H of the system in front of the minus T delta S. So then it's minus T delta S universe equals delta H system minus T delta S of the system. So why did we do that? Well, we did that just because it looks a little nicer and it's a little easier to see with that delta H minus instead of the minus thing plus the delta S. But the other thing it did is we now are calling minus T delta S universe the Gibbs free energy, and that has the designation of delta G. So this is our new term that we're talking about now, is Gibbs free energy. And what Gibbs free energy does, it shows that it ties together that delta H and delta S values. So now we've got heat and we've got randomness in the same equation. And so that final equation is delta G equals delta H minus T delta S. So we kind of walked through how we got there. Hopefully that made sense to you. If it didn't, take a look at it. But really the takeaway here is this last one, the Gibbs free energy expression, where we have delta G equals delta H minus T delta S. As you probably can imagine, that's a formula. We're probably going to use it for calculations, and we'll go through some of those. But that's the main takeaway from this slide. So what's the implications of this Gibbs free energy, this delta G? So, and this is something you should know. If delta G is negative, the forward reaction is spontaneous. If delta G is 0, the system's at equilibrium. And if delta G is positive, the reaction is non-spontaneous. But if it's positive, then the reverse reaction would be spontaneous. Okay, so delta G negative, the reaction's spontaneous. Delta G zero, it's at equilibrium. The system's at equilibrium. Delta G positive, reaction is non-spontaneous. So we go back, we look at our formula down here of delta G equals delta H minus T delta S. If we use that and we do some type of a calculation and we get a negative delta G, we would know that that reaction is spontaneous. If we get a positive, we know it's not spontaneous. So you can calculate standard free energy changes, and it's pretty similar to the delta H calculations and the delta S calculations. It's the same idea. In this case, it's delta G, but it's products minus reactants. So you sum up all those delta G values of the products, and you subtract from that the sum of the delta G values of the reactants. Once again, when you do this type of calculation, you need to have a balanced chemical equation, because just as with delta H and delta S calculations, you need to incorporate whatever the coefficients are from the stoichiometry of the reaction. So whether it's a delta G calculation, whether it's a delta S, a delta H, it's really the same type of calculation. Obviously, the big difference is you're using those different constants, and in a homework problem or an exam or something, they would be given to you, or they would be in a table that you could look them up. But that same basic way of doing the calculation is consistent across all three of those. So when they calculate these standard free energies, there are some assumptions made. Is that if it's a solid, the standard state is pure solid. If it's a liquid, the standard state is pure liquid. If it's a gas, the standard state is 1 atmosphere. Solution, 1 molar concentration. And for an element, the delta G formation is 0 for when it's in the standard state. Okay, so here's a good table. So this table that we have here ties together what we've been saying about delta H, delta S, and delta G. And so if you're going to memorize one slide out of this chapter, make sure you memorize this one. Because what we're saying here is, we're saying what happens when you have positive or negative signs for delta H and delta S in terms of, is a reaction spontaneous or not? And so remember, we said if delta G is negative, the reaction is spontaneous, right? So in this first example, we have a negative delta H, a positive delta S, and then that results in a negative minus T times delta S. So what you're doing here is you're looking at the effect of delta H and delta S on the signs of these two terms, the delta H and then the minus T delta S terms. And based on whether it's positive or negative, that tells you if the delta G is positive or negative, and then it'll tell you if it's spontaneous or not. So in this first one, having a negative delta H and a positive delta S results in a negative T delta S and a negative delta H. So if both of those are negative, we're in good shape. We're going to be spontaneous. We go to the next example. If we have a positive delta H and then a negative delta S. Well, if the delta S is negative, then minus times a minus gives us a plus for that T, that minus T delta S term. So then delta G's got to be positive. So then we would know, doesn't matter the temperature, it's not spontaneous, okay? We get to these next two, and the first one, delta H is negative and delta S is negative also. And then the last one, they're both positive. Well, depending upon the temperature, it can wind up being positive or negative. And so when they're both, delta H and delta S are both negative, it's spontaneous at low temperatures, it's non-spontaneous at high temperatures. What does high, what does low mean? We don't know exactly because it depends on what the actual numbers are. The last one, where spontaneous is spontaneous high temperature and non-spontaneous at low, once again, we don't know exactly what those temperatures are because we'd have to know the values for delta H and delta S in addition to the sign. But this idea of seeing the impact of delta H and delta S in terms of is it positive or negative, and then in these last two, seeing how temperature factors in, that allows us to determine if delta G is negative or positive, and then tells us if the reaction is going to be spontaneous or not. So once again, getting comfortable with using this Gibbs free energy formula, the delta G equals delta H minus T delta S, using that and then using those terms of delta H and delta S being positive or negative helps us predict whether the reaction is going to be spontaneous. In my mind, it's kind of like similar to some of the equilibrium stuff we did, where we would say, oh, if the equilibrium constant is big or little or whatever, then that means you have more products or more reactants or things like that. It's great to plug the numbers in and actually do the calculations. We all love calculations, right? That's fun. But really, this is even better, I think, because it gets you conceptually understanding just kind of the impact of these terms, okay? So we mentioned the third law of thermodynamics, but then that led us to the Gibbs free energy, and the Gibbs free energy now has us tying together in a formula, heat flow, which is delta H, and then the entropy, the chaos. This is kind of what we were just saying. How does delta G change with temperature? Well, we want it to be negative, right? So obviously big temperature values make this term more negative, the T minus the T delta S term more negative. But it really does get down to what are those actual values of delta H and delta S. So conceptually, increased temperature increases spontaneity. And in general, that's kind of true of reactions. If you think about it, you go to the grocery store and you buy something and you're not going to use it for a while, what do? You put it in the freezer, right? You put it in the freezer because that slows down the reactions and then it lasts longer. If you set it out on the table and leave it there where it's warmer, it spoils quicker. That's really what we're saying. That's when you lower temperature in general, reactions slow down. And so the high temps lead to spontaneity. That kind of makes sense. At least to me, it does. Okay. You can find a free energy change. So once again, delta G, by incorporating equilibrium into it. And so here we have an expression for that. So we have delta G equals delta G naught plus RT times the natural log of Q. Q is that, remember, that's the term we introduced when we were talking about equilibrium. It's still products over reactants, but it's not at equilibrium. It's at whatever the conditions are then. Okay, so that Q is the same one we had in the last few chapters. So at equilibrium, Q equals K. We all knew that, right? Because that was our definition of it when we did the equilibrium section. And then at equilibrium, delta G equals 0. We had said that earlier. In that case, the equation then becomes 0 equals delta G plus RT times natural log of K. And rearrange it, we can get delta G naught equals minus RT minus RT times the natural log of K. You can rewrite that expression with the one at the bottom here, K equals E to the minus delta G naught over RT. So this is another example of an equation that we will use to do some calculations in the homework. Okay, so let's talk about the relationship between delta G naught and the equilibrium constant. So the more negative delta G is, the larger the K is. Does that make sense to us? If delta G is negative, we said that's spontaneous, right? And if K is big, that means more products than reactants. So that kind of makes sense. Good. If delta G naught is positive, then K is negative. And if delta G is 0, then K is 1. So once again, if it's 0, K is 1, that's the equilibrium. Okay, so there is some homework I'd like you to work on, and here's some problems I would suggest you take a look at. I'd like to go over a couple of these. So the first one is 1957. So in this case, you need to use Appendix C in the textbook. And in that appendix, they have values for delta H naught, S naught, delta G naught. And you use those values, or whether you use those values to calculate them. So for the reaction. So in the first one, so we have our balanced equation at the top, H2 plus F2 going to 2HF. So let's calculate delta H first. So we can go back in that table and look up the formation constants, the delta H formation for each of these things. And so products minus reactants. So the products, HF, we get a value there of minus 268.61 kilojoules per mole. We have 2 moles of that in our balanced equation. So we're going to multiply that delta H of formation by 2. So that's our first term, okay? We only have the one product, so there's nothing else to add there. Then we'll subtract from that the sum of the delta H of formations for the H2 and the F2. So you go ahead and look those up in the table, and those are both listed as 0. So we have the 2 times the minus 268.61 kilojoules per mole minus 0 plus 0 for a value of minus 537.22 kilojoules as our delta H. Okay, now we want to calculate delta S. As I said before, all of these calculations are pretty similar. You're just using the different constant values. So once again, products minus reactants. In this case, it's 2 times 173.51 joules per mole Kelvin. The second part for the reactants, though, the H2 and F2 actually have values for the delta S. So we have positive 130.58, and we add to that 202.7. We sum those up, and that gets subtracted from the sum of the products. If we go ahead and do that math, we get 13.7 joules per Kelvin. All right, and then finally, the last one, delta G, we actually can do that one two ways. So we're going to do it both ways. And we'll see if we get the same answer. In theory, we should. In practice, you don't always get the same answer. So we could go ahead and calculate delta G, similar to how we did delta H and delta S, because we can look up the individual delta G formation values for these compounds. And so if we do that, our products, we have 2 times its delta G of formation values minus 270.7. And then for the reactants in this case, the H2 and F2, those values happen to be 0. So we could go ahead and do that math and get minus 541.4. So let me ask you this question, is that reaction spontaneous? Yeah, because our delta G is negative. So technically we're finished, but let's go ahead and remember we had this other formula that related delta H and delta S to delta G. And we can use that one also to solve for some of these things. And so let's go ahead and solve for delta G. We have our delta H value that we found in the beginning. We have our delta S naught value, which we found here in the second part of the problem. And let's go ahead and plug those values in. So we'll put minus 537.22 kilojoules into the delta H value. Our temperature was 298 Kelvin. So we have that to put in for T. And the only thing we have to be careful about is our delta S value had units of joules per Kelvin. So we need those units to be the same for delta S and delta H. And since we went ahead and put kilojoules with the delta H, we need to change our units on delta S to kilojoules. And we can do that simply by taking that 13.7 joules value and multiplying by 10 to the minus 3. So now it's kilojoules. So now we've got kilojoules minus kilojoules, which is what we want, because this temperature, this 298 Kelvin, is going to cancel out the Kelvin in that second term after the minus sign there. So we go ahead and do that, and we get a value of minus 541.3 kilojoules. Before we got 541.4, pretty doggone good agreement there. So that's nice. Like I said, it doesn't always work that nicely, but in this case it did. So just to talk again about what we did here, we had a balanced chemical equation. And why was that important? It was important because we needed to know what those coefficients were in front, because we're going to use those when we do these delta H, delta S, delta G calculations. If you take a look at those 3 calculations, the first 3 we did, they really should look pretty much the same calculation, right? Products, sum of products minus the sum of reactants. You take into account that coefficient in front of each of the molecules that's involved. And then after that, you just have to make sure you looked up the right constants to use to plug in. You did all that stuff, you get your answer. If you wanted to use this bottom formula, which sometimes we do depending upon the information that you're given, the key thing there was making sure that you had your temperature in Kelvin and make sure that your delta H and delta S values have the same energy units. If you're working in joules, that's fine. If you're working in kilojoules, that's fine. They just both have to be in that. And like I said, It is a bit strange because a lot of times, well, usually the delta S value is in joules and the delta H is in kilojoules. So you just got to make sure you change one of the two to make sure that matches up. Okay, any questions about this? All right. Let's take a look at another one of these. So in this case, we have graphite plus 2CO2 going to CCl4. So we have our balanced chemical equation up on top. Okay. And so the thing that jumps out to me on this is that the Cl2 has a coefficient of 2 in front of it. So that's going to show up when I do my summations of products minus reactants. So once again, delta H, as we said before, products, you look up the delta H value for carbon tet, minus 106.7. That's the only product. So then we'll subtract from that the sum of the reactants. The carbon has a value of 0. The Cl2 has a value of 0. I went ahead and wrote the 2 in there just so I get in the habit of doing that, because maybe some of the others won't be 0. And then I go ahead and it's trivial math because obviously a number minus 0 is that number. So we get minus 106.7 kilojoules for delta H. We then move on to delta S, same idea, products minus reactants. In this case, we do have some values, some delta S values to plug in for the reactants. We have 5.69 for the graphite, and we have 222.96 for the Cl2. I remember to put my 2 in front of that. Once again, that comes from the coefficients in the equation. And then I can go ahead and solve that and get minus 142.2 joules per Kelvin. And then finally, the third one, delta G, that same process, products minus reactants, summing those up. In this case, similar to delta H, the reactant terms were both 0, so that delta G value just essentially equals the product value. So if in this case, we go ahead, found those 3 values using this products minus reactants type and the values in the table, but we also could use our delta G formula. So we can go ahead and plug in the value we found for delta H and the value we found for delta S, remembering in this case, I converted my delta S again to kilojoules so that those both would be in kilojoules, the delta H and the delta S. Temperature was 298 K, and I get minus 64.3 kilojoules. So once again, pretty good agreement on those two. So you could continue on. There's a couple more of those to do. I think hopefully you're kind of getting the idea of that. So I'm not going to go on and do the same one again. But I would like to move on to 19.75. And in 19.75, you're asked, does delta G increase, decrease, or stay the same when the partial pressure of oxygen is increased? So if we think about that, what's our delta G formula? Delta G equals delta G naught plus RT times the natural log of Q. And remember, Q is that equilibrium expression with products over reactants. So what we want to do in each of these cases is take a look at what our balanced equation is. So in the first example, it's 2CO plus O2 going to 2CO2. So if we go ahead and write our Q expression out as products over reactants, so CO2 concentration divided by CO concentration times the O2 concentration. Then we go back and take a look at the stoichiometry and the balanced chemical reaction. And we see that on 2 of those, we have coefficients of 2. So the CO2 in our numerator, we need to square that. And then the CO in our denominator, we need to square that. And so we were asked, what's the impact of O2 on this? So O2 is down here in our denominator. So if O2 is getting bigger, what happens to Q? Bigger or smaller? Gets smaller. So if that second term, which we're adding to the delta G naught, is getting smaller, we don't know by how much because we don't have actual numbers, but we know conceptually it's getting smaller, then that tells me that the delta G is going down, it's decreasing. So that's the kind of logic that you want to apply to this. Let's take a look at the next one, B. 2H2O2 going to 2H2O plus O2. We can set up an equilibrium expression, products over reactants. This time the O2 is in the numerator. So if that's getting to be a bigger number, then that Q value is going to increase. And so then that's going to result in delta G increasing. And then finally, the third one, similar thing again, we write our reaction out, we balance it. But the key is really where is the oxygen, which is what we're interested in, where is that showing up in the equilibrium expression? Once again, it's in the numerator. So if that's pressure, that concentration is increasing, then Q is getting bigger, and by association through the formula, the delta G is going to get bigger. So while it's a different type of calculation, the thinking is similar to what we did with the equilibrium stuff back in the equilibrium chapter, right? You set up these expressions that represent equilibrium, and then you see if stuff in the numerator is increasing, then you're increasing things overall. If stuff in the denominator is increasing, then this delta G value goes down. Okay? Let's look at 1979. So in 1979, we're once again going back to Appendix B, and we want to calculate the equilibrium constant and delta G at 298 K for these reactions. Okay, so the first reaction is H2 plus I2 going to 2HI. And so if we want to find delta G, and we want to find K, that equilibrium constant, well, delta G, we've done that a few times already, right? We know we can do products minus reactants and get a delta G value for that. If we get that delta G value, then we can use our delta G equals minus RT natural log of K expression to solve for K and get the equilibrium constant. So that's what we're going to do. So delta G, products minus reactants, some of the products minus some of the reactants. We use that data that's in Appendix C that they referred us to. And so we have 1.30 kilojoules per mole of for the HI. There's a coefficient of 2 in the balanced equation. So we have to multiply it by 2. And then we subtract the values that we look up for H2 and I2, which happen to be 0 and 19.37. And we get a value, a delta G value of minus 16.77 kilojoules. Or if we wanted in joules, minus 16.77 times 10 to the third joules. Well, great, we've got our delta G value. So now we can use this relationship, this delta G naught equals minus RT natural log of K. We can plug in that delta G value that we had before. We needed to put it into joules because of this constant, the 8.314 joules per Kelvin constant, okay? That's why in this case, we couldn't leave it in kilojoules because of the constant that this R represents, the units on it. And then we were told it's 298 Kelvin. So now we can start working through the math. We get to where we're 6.79 equals natural log of K. We raise that e to the 6.769 to do the anti-log, and then we solve for K. So make sure you know how to do this step, this e to the 6.769 type of calculation on your calculator. So if you're a little uncertain about it, make sure you practice a few times and make sure you can do that. So let's just take a look again at the logic in solving this problem. We had a balanced equation. That was important because we wanted to get those coefficients for each of the products and reactants. We could find delta G naught from the delta G values that were given in the appendix, okay? And like I said, you always got to be given those values. And we did the products, some of the products minus some of the reactants. Similar to what we do for delta H, similar to what we do for delta S. All this is a similar type of process to do that calculation. That allowed us to get a delta G value. So we have that delta G naught, and we can then plug that into this, our relationship between delta G naught and the equilibrium constant, that formula that we have. We plug that in. We know our constant value for R is 8.314, 298K, and now we're simply solving for natural log of K. The one thing we had to remember was to have our delta G units and our constant units both be in joules. So we did have to do a little bit of change to our calculated delta G naught value because the values we'd gotten out of the table were all kilojoules. So we had to make sure those were in joules. The final thing was making sure we knew how to use our calculator to do this e to the whatever type of calculation. So let's do another one of these. Let's do the next one, which is 2H2O2 going to 2H2O plus O2. Oh wait, never mind, that's the wrong problem. It's C2H, so it's ethanol going to ethene plus water. So products over reactants. To find our delta G, we look at our balanced equation and they're all coefficients of 1. So basically it was just looking up the values in the appendix, putting them in, summing the products, the C2H4 and the H2O, minus the reactants, which is minus 168.5 for the C2H5OH. We can then get a delta G value. We change that into joules and then plug into our delta G naught equals minus RT natural log of K. Once again, go through that math. We have our e to the, in this case, it's a negative value. Solve that to get 0.0390. And then the last one is going to be similar. So I'm not going to bother going through that. You guys can work on that. But hopefully you get the general idea there. Any questions about any of this stuff? Okay, so just a reminder, Tuesday, so next time we meet in class, we'll start the class with a little bit of electrochemistry, and then we will have a quiz on this chapter 19 stuff. So this thermodynamics chapter, okay? So now what I'd like to do with the remainder of the time is talk a little bit about electrochemistry and start on that chapter. So let me pull that up. Okay, so hopefully you can see the chapter 20 slide. If not, let me know. Otherwise, I'll assume you can. So I think you guys did some redox type chemistry stuff in lab recently, is that correct? So hopefully some of this will be familiar to you as we talk about it. So let me just get rid of this thing. So when we talk about electrochemistry, we're talking about how electricity can be used to do chemical reactions and how that all fits in. That's really what you're talking about. And there's, just as with most things, there's spontaneous and non-spontaneous processes, and we'll talk about that a little bit. So let's talk some definitions here. So in the most basic sense, we have oxidation and reduction. And what does that mean? Oxidation simply means loss of electrons. Reduction means gain of electrons. So if oxidation is occurring, something's losing electrons. If reduction is occurring, something's gaining electrons. So there's more detailed definitions of oxidation and reduction, but this is really the base of what it is. This is always going to be true. One of the things you're going to have to remember, because we did talk about this, I think it was last semester, are oxidation numbers. So if you didn't remember that, well, this is your chance to get a second shot at it and learn it this time. So just some general guidelines when assigning oxidation numbers. If it's an element, the number is 0. If it's a monatomic ion, then it's the charge. So if it's like Fe plus 3, then it's plus 3, okay? If it's Cl minus, it's -1. Oh. So when we look at now the atoms in a molecule, regular molecule, fluorine is always -1. Oxygen is almost always -2. If it's a peroxide, then it's -1, but that's the only time. Hydrogen, almost always +1. If it's a metal hydride, it can be -1. The sum of the oxidation numbers has to equal the overall charge of the compound. Okay, and if it's a regular compound, not any kind of ion or anything, then that value is considered 0, all right? So it doesn't seem like you get a lot of guidance here, but this is usually enough to figure out what the oxidation numbers are. And we'll do enough practice where I think it'll come back to you if you've kind of forgotten what it is about. Okay. So why do we use oxidation numbers? Well, the oxidation numbers is like a bookkeeping way of keeping track of what's losing electrons and what's gaining electrons in terms of the atoms involved. As the oxidation number increases, that means you're losing electrons. So in other words, if you have something starts at 0 and then goes to +2, that's lost electrons, right? Because you have that +2 charge, because electrons are negatively charged. So if you take away 2 of the negatives, then it's positive. So oxidation number increases, it loses electrons for an element. That element, we say, has been oxidized. If the oxidation number decreases, in other words, you gain electrons. So if we say chlorine, for instance, goes from 0 to -1, that would be gaining electron because we've got more negative charge. Then we would say that element is reduced. We said earlier that oxidation means loss of electrons. It also can mean gain of oxygen or loss of hydrogen. We said before reduction was gain of electrons. Well, it also can occur when you lose oxygen or gain hydrogen. So this kind of expands the definition a little bit of oxidation and reduction. The other thing I want to remind everyone is that if you have oxidation, you got to have reduction and vice versa. They always occur together. You can't just have one occurring. So if something's oxidized, something else has been reduced. So personally, oxidizing agents and reducing agents always are a little confusing to me, and I have to think about them a little bit. But oxidizing agents, they gain electrons readily. They bring about oxidation of other substances by being reduced themselves, and they are reduced in an oxidation reduction reaction. So if something is reduced, it's an oxidizing agent. And then vice versa for the reducing agents. Reducing agents lose electrons. They can bring about the reduction of other substances by being oxidized themselves. And then they're oxidized during an oxidation reduction reaction. So if something's oxidized, it's a reducing agent. If something's reduced, it's an oxidizing agent. I don't know why, but for me, I find that confusing. So I have to think about it every time I say it. So we're going to go through this again for a second here, because this is understanding these definitions is really the bulk of the first part of the chapter, is just understanding oxidation and reduction, what we mean by that. So if you understand it and you get it, great. If you don't, please spend some time to kind of think about it and try and memorize some of this stuff. So we say something is oxidized when it loses electrons. And so here's an example of zinc. Loses 2 electrons to become zinc plus 2. So the way I always think of it is oxidized means that number gets more positive. So in this case, went from zinc neutral to zinc plus 2. So plus 2 is a bigger number than 0. We can have a species reduced when it gains electrons. In this case, we have hydrogen going from a plus charge, and now we have H2, so it's picked up an electron. So now it went from plus to 0. So you basically have subtracted the charge from a +1 down to a 0. So you reduce that charge number. And that's because it picked up electrons. Electrons are negatively charged, so it comes out of that. So an oxidizing agent causes something else to be oxidized. A reducing agent causes something else to be reduced. Here's just an example of how you would do that linkage of oxidation states changing. So this is the reaction we were just kind of looking at. And on the left-hand side here, we have zinc initially. It's in the 0 oxidation state. And then over on the right, now it's in +2. So we said before that if it's a simple ion like that, that its oxidation state is simply that charge, so it's +2. Zinc is that solid state is 0. So we see here, went from 0 to +2. So that means it's oxidized, right? That oxidation number went up. The other reactant was hydrogen plus. Well, that's that ion with a charge, so it's a +1. It goes to H2. There's no charge there, so that's a 0. So going from +1 to 0, that we've reduced that value from +1 to 0. So in that case, the H plus has been reduced. So it's this kind of thinking that you'll use when you look at these reactions and looking at the individual. This one's pretty simple because we just have 4 atoms, but in other ones you'll have maybe a little bit more atoms, and we'll go through some of those. Okay, so in oxidation reduction chemistry, which is called redox chemistry, you talk about these half reactions all the time. And the half reactions are just breaking out the reaction that demonstrates the reduction part and the other reaction that demonstrates the oxidation part of the overall reaction. Because remember, we said you can't have reduction without oxidation and vice versa. So if you have one, you're going to have the other. So when we do this, we write the oxidation and reduction reactions separately, and we call these half reactions. And then we balance them separately. And then at the end, we'll combine them to write our overall redox reaction. So let's take an example here. We have Sn plus 2, 10 plus 2, and Fe plus 3, iron plus 3, and we're saying they react. So we're told that Sn plus 2 goes to Sn plus 4. Here we have plus 2 on the left-hand side, plus 4 on the right-hand side. To balance the charge, so we've got plus 2, plus 4 on the other side. We have to add 2 electrons to the right-hand side of this. So now we have minus 2 and plus 4 for an overall plus 2 on the right-hand side. And then we have overall plus 2 on the left-hand side. So that balances out. For the reduction part, we have Fe plus 3 going to Fe plus 2. In order to get things to balance, we wind up with a 2 in front of each and then 2 electrons on the left-hand side. So balancing redox equations. There's something called the half reaction method, and these are some guidelines on how to do this. I guarantee you balancing these redox equations will be on the exam, okay? There is 0 chance of not having to balance some of these. I will also tell you that balancing redox equations, there's only one way to get good at it, and that's to practice. Because there are so many opportunities to make a mistake when you're balancing that you got to just kind of get used to doing keeping track of things, and it's more of a bookkeeping exercise than anything, I think. But you really got to kind of focus and keep track of stuff. And like I said, the only way I'm aware of getting able to do this is to do some practice. So there's going to be some homework problems assigned. I strongly suggest that you spend some time working on those, because that'll be very helpful. The good thing about these kind of problems, when you're finished, you know if it's right or wrong, because you can go back and check and see if the left-hand side balances with the right-hand side. If it does, you got it right. If it doesn't, it's not right. And so here are some rules. And here's a slide. As I said on the last chapter, there was a particular slide. I said, yeah, you should know this. You should know this slide. So to do the balancing, you make the 2 half reactions, the oxidation reaction and the reduction reaction. You have those separated out. Then you balance each of them independently. So first you balance any atoms other than oxygen and hydrogen, okay? So by balancing, we mean that's where you put some coefficient in front of the molecule to make it balance, to make that atom balance on both sides of the reaction. Then the next thing you do is balance the oxygen atoms. And you do that by adding water, so H2O, to the side that is deficient in oxygen, okay? Obviously, if you add water, that's going to mess up your hydrogen balance. So then that's where you use H plus on the other side from where you added the water to balance out the hydrogens, okay? So if you did all this correctly, you should have the non-oxygen and hydrogen atoms balanced. Then you should have the oxygens balanced. And finally, you should have the hydrogens balanced. And then the last thing to do is you have to balance the charge. And you do that by adding electrons. So balancing the charge means you go through and you look at the stuff on the left-hand side and the stuff on the right-hand side. If you got any ions, there's a good chance you will. If it's a cation, that's positive. If it's an anion, that's negative. If there's coefficients in front, you got to take that into account. And you want to make sure that at the end of the day, the charge balances left-hand side, right-hand side on that half reaction. Remember, electron is negative, so that's a negative charge you can add. So you can then, if you have, say, +5 on the left and +3 on the right, if you added 2 electrons to that +5 side, then that would reduce that overall charge to +3. So you do this process for each of the half reactions. Most of the time after you do that, the electrons don't balance between the two half reactions. Sometimes you get lucky and it does, but usually it doesn't. And by that, what I mean is you'll have one that the individual half reaction balance is fine, but there's like 5 electrons, and you do the other one and there's 2 electrons. So you think, gosh, I'm done. Well, you're not done. This is where you have to multiply them by factors to make the electrons equal so that they cancel out on the 2 sides of the reaction. And we'll go through and do that in an example, which makes it a little easier to see. And then once you do balance those electrons out, then you add the 2 half reactions together, and then you check to make sure everything balances. And that's where I'm saying, that's where you'll find out, did I do this correctly or did I not? Okay. Any questions on this? This approach works as written for acidic solutions. We'll talk a little bit later about basic solutions, and there's a slight variation that you do for the basic solutions, but we'll talk about this. It's kind of the same idea, but there is a slight twist to it, because obviously, if it's a basic solution, you're not going to be adding protons and have protons at the end, or it would be an acidic solution. So you have to do something to correct for that, but don't worry about that for right now. I just wanted to mention that though. Because in the homework, some of them are basic and some of them are acidic, and anyway. Okay, so I think I'm going to stop there, because this is starting to look at to balance this equation. So we're going to balance this equation that you see here, this MnO4, it's C2O4 minus 2. And I don't want to get started on that, then have to stop. So I think we'll pick that up next week. So just to remind everyone, quiz on Tuesday. We'll start with continuing the redox chemistry chapter, the electrochemistry chapter on Tuesday. After we do a little bit of lecture, then we will go and have the quiz on Canvas on chapter 19. And then on Thursday, we'll pick back up with the electrochemistry. Just to remind everyone again that the final exam for this class is Thursday, May 6th from 8 to 10 a.m. And that is Canvas online final exam. So any questions about anything before we end? Okay, thank you.